Welcome to this session about MPI, which will be presented by Louant from Liège.
So thank you, Damien. Hello, everybody. I hope that you are well and safe. So the topic of today will be MPI, and in particular, programming distributed memory system. And we will start with a short introduction and motivation on why we wish to program parallel. We wish to program in parallel, as well as the different type of paradigm to program parallel machine. So from the 70s to the 90s, everything was well. It was what we call the free lunch period, where the frequency, number of transistor, and single thread performance of the CPU was increasing over the years. And so you can write your code and just wait for a certain amount of time, and you will increase the performance of your code just by changing the hardware, because the hardware is way more powerful. But late 90s and the beginning of 2000s, as you can see, the single thread performance of the CPU start to reach a plateau, as well as the frequency. Because of course you reach physical limits and you cannot increase the frequency as you wish, because then the amounts of heat that you will produce will increase accordingly. And so what the CPU manufacturers start to do is increasing the number of cores instead of driving the single thread performance and the frequency of the CPUs. And as I say, they ran out of room to boost the CPU performance, and instead of driving the clock speed and straight line instruction through, they just turn to hyperthreading and multi-core architectures. And during the 90s, what also appears is some standards to program this parallel machine. And the first, which will be the topic of today, is the MPI standard that was introduced in May 1994 and updated in 1995 by the MPI Forum, which is a group that defined these standards. And around the same time, you also have OpenMP, which was introduced in 97 for the Fortran specification and 1998 for the C++ specification. And these standards, the MPI and OpenMP standards, allow for a different paradigm of parallel computing. The first one is shared memory. So it's a system which has at least one multi-core CPUs, and all the CPUs have access to a single memory address space. And you may have a multiple CPU on the same board, and each of these CPU may have multiple cores. And the system memory may be physically distributed, but logically shared. What I mean by this is that some of the cores or some of the socket may have affinity for some part of the memory, but inside the operating system, a program can access the whole memory through inter-socket connection, even if physically this memory is separated on the board. And this kind of system, most of the time, is programmed using threads, which are independent stream of instruction, and multiple threads can exist within one process. So one application will start, which have some data of open file, open library, as well as a code. And inside this application, you have multiple threads that can run in parallel, and they own only the bare essential resource to exist as executable code. It means that only the execution counter, stack pointer, register, and thread-specific data. But the whole memory of the application is available to the all threads. So when you do a malloc or allocate in Fortran, you allocate memory that is shared inside the process to all the thread. And in scientific computing, the dominant paradigm to program this kind of system is OpenMP. On the other hand, and this will be the topic of today, you have distributed memory system. So it's multiple nodes, so multiple machines, multiple servers that are interconnected by an high-speed network. And the nodes consist of processors, multiple cores, and local memory, so memory installed on each node. And this kind of system, the memory is local to each node, and in order to access data from another node, you need to have communication through the network, and this communication is done via message passing. And the message passing is a communication between processes. So processes, if you simplify it, is an instance of an application, and processes have at least one thread, which is the main thread, but it can have multiple threads, as we have seen before. And this process is just a container describing the state of the application, the code, the memory mapping, and shared memory, shared library open or file open. And in scientific computing, for this kind of paradigm, so distributed memory system, we use MPI, which is message passing interface. So MPI is a standard. In itself, MPI is no more than a lot of paper when where the name of the function and what they're supposed to do is described. So it's just the description of a communication protocol for programming parallel computers, and in particular distributed memory system. And this function that is described in the standards allow for both point-to-point and corrective communication between the processes. But what MPI is not is a language. It just defines a library, okay, and you will link your program with this library, and this library allow you to do message passing. But an MPI program are compiled with ordinary compilers, and then the compiler will link to the MPI library. So sometimes it's confusing because you have a kind of a utility, which is MPICC, we'll see that later, which looks like a compiler, but in itself, it's not a compiler, it's just a wrapper to call a host compiler behind it. And what MPI is not also is a particular implementation. As I said, it's a standard. So it's just a list of functions, a list of constants, and nothing more. Then the people are free to have their own implementation of the MPI library. So they will take the standard and read the description and write a library that will behave according to the standard. So most of the HPC vendors provide an MPI implementation. Sometimes it's from scratch, or they use one of the open source implementation and modify it. And of course, you have the free open source implementation like OpenMPI that are available. And MPI was the reason why MPI was created is that before that, HPC vendors created their own library for message passing for their system, and it was proprietary solution. And most of the time, there is no interoperability between the two different implementation of a message passing library from different vendors. MPI changed that by standardizing the library, and so each implementation, if it's compliant, you can compile your program, link it with the library, and it should run with any implementation. It can be the Intel MPI library or the Open MPI library. It will not change anything. Your program should be able to run if the implementation is up to the standards. The idea between MPI, most of the time you will program using the single program multiple data model, SPMD. And the idea behind this model is that multiple parallel processes run the same program. So you will start your application multiple times and they will run in parallel. So you have multiple processes, and then you have to make sure that you can identify uniquely these processes. And so the MPI library provide a way to get the ID of your process. And so you can, with this ID, you can choose what this process will do. And as this is processes, they have their own memory space. You cannot share variables directly between the processes. You need to have communication between them in order to have copy of the data from the memory space of one process to another process memory space. And depending on the identifier of the process that run in parallel, you can follow different control paths. And this is the core idea between a program using MPI. So as an example, we have one program and we run it in parallel with two processes. And depending on the identifier of the programs, they can start directly to have some work on some piece of data until one process is in need to communicate with another. And in this example, process 1 send the request to process 2 saying, okay, I am ready to send you some message. Are you ready? But at that time, process 2 is not ready. He's still doing his own work. And when he finishes work, he sends a receive request to the process and say, okay, I am ready to receive the message that you want to send me. And then communication occur and a message, so a part of the data copied in from the memory of process 1 are copied to the process 2. And as you can see, this is a collective process where both process 1 and process 2 are involved. Process 1 need to say, okay, I'm ready to send data, and process 2 need to be ready to receive said data. And after communication, both the process can go back to their own part of the work and continue. And the process as just described can be summarized in 6 functions. The first one is for initializing the environment in which we execute our program. And then we have 2 functions that allow us to discover who we are and how many processes are working on the data or on our problem. So we have one function, comSize, which allows us to know how many processes are running in parallel, and a second function, which is MPI comRank, which allows us to determine the identity of our process. And then, of course, you have a function to communicate, which is MPI send to send a message and MPI receive to receive a message. And after you finish, you need to finalize your environment, and you use the MPI finalize function. So let's dive into the basic, but before that, you are free to ask questions in the chat if you have any about what we have seen so far. But it looks like it's very quiet. Okay, so MPI basics. So the first one is about initializing and finalizing the environment. To initialize your MPI execution environment, you have first the MPI init, and you have there the declaration of this function for C and Fortran. And in these functions, you need to call it once and before any other MPI function call. So each process needs to call this MPI init function, and you need to do it before any MPI function call. If you don't do that, your application will crash. And in C, you can see that this function takes 2 arguments, which is basically a pointer to the argument of the main function. These arguments are completely optional. You can pass a null pointer if you want. It's just there in case they are needed in the future, and some MPI implementation use them, but it's not in the standard. So it's just future-proofing that the people that design MPI put there, but you can pass MPI init null if you wish in C, and it's not a problem. These arguments are not very important. In Fortran, you have an integer which intends out which is an error, but I will not discuss this right now because it's in the next slide. And then next step, at the end of your application, you have the MPI finalize, which will terminate the MPI execution environment. And once you have called this function, you may not call any MPI function from the library anymore. So your MPI execution environment is completely dead. So you do some cleanup and you cannot use MPI anymore. So with this function, the idea is that, for example, in C, you have your main function and you call MPI init as fast as possible, and you call the MPI finalize function at the end of your main function just before returning the application return value. And as you have seen in the previous slide, we have I error in MPI that is present for the MPI init and MPI finalize. And this is the error. And all MPI routine return an error value. In C, this is the return value of the function. And in Fortran, it's returned as the last argument. So you have a lot of possible error. This is the most common. So basically, most of the time, you check if the return code is MPI success. If it's MPI success, you are very happy. It means that everything goes fine. The exception to the rule that every function in MPI return integer, which is an error, is the MPI wall time function, which allow you to measure the time between 2 points in your application. This is the only exception to this rule of MPI function return an error. And this function return a double, which is a timestamp. And if you do the difference between two timestamps, then you have the time elapsed between 2 points in your program. So it's quite useful when you are testing the performance of your application and if you want to time your application. Now, to have communication, you need something that may describe the people with whom you want to speak. Okay, and in MPI, this is a communicator. And a communicator represents a group of processes that can communicate with each other. An MPI application can create multiple communicators, so subgroups of processes, but most of the time you will use the MPI Comworld communicator, which is an communicator which allows you to communicate with all the processes. So it's just an object that describes a group of process, and this group of process know how to communicate with each other. But inside this communicator, you also need to identify the processes. And it's done by an integer, it's a number. So if you have 4 processes, you will have numbers that will represent these processes, and you have 0. Oh, sorry. I will take the question afterward. When I finish this part. A communicator, so each process inside a communicator is identified by a number. If you have 4 processes, you will have process 0, process 1, process 2, and process 3. And this is called a rank in MPI. And each process is uniquely defined. The rank is uniquely defined inside a communicator. But if a process is present in multiple communicators, it may have different rank for each of the communicator it is part of. So, for example, if we have 3 processes and we have 2 communicators, so the first communicator, which is the default MPI world, is the communicator that will represent all the 3 processes that we start at the beginning of the execution. And inside this communicator, process 1 will have rank 0, process 2 will have rank 1, and process 3 will have rank 2. On the other hand, if you have another communicator, communicator 2, that is including process 2 and process 3. Inside this communicator, process 2 that has the rank 1 in MPI world then become rank 0 in this communicator. And the same apply for process 3 that was rank 2 in MPI world and become ranks 1 inside this communicator. And the MPI specification, as I said, provide the default communicator, which is set up at the startup of the application, which include all the process started. And this is MPI world, and this is probably the communicator that we will use the most when you write your application. Inside the communicator, you have two interesting functions, which is MPI size and MPI world and MPI rank. The first one, MPI size, allow you to know the number of process that has been started and is present in a communicator. So in C and Fortran, you pass the communicator on which you want to have the size, and then you have in C a pointer, and this pointer will be filled, the value of this pointer will be filled with the size at the return of the function. And in Fortran, you have this side with intent out, and of course in Fortran you have to add the I error at the end, which is not present in C because it's returned by the function. And then you have the rank, which allow you to find out which process you are. It's exactly the same signature. You have you pass a communicator, and in C at the end of the function, you have the rank stored in this for the value of this pointer, and in Fortran this is a value with intent out. So this is how you get the size of your communicator. So how many processes there are, and how you get for each individual process the rank, so the identifier of this process inside the communicator. And as an illustration for this, we have the classical Helloworld program. And this program is quite simple. First, we initialize the MPI environment, okay? And for having the signature of this function, of course, we have included mpi.h, which is the header file for C. And in Fortran, we use the MPI module. Once we have initialized our application and our MPI environment, we need to know what's the size of or MPI world. So how many process has been started for our application. And we do that with the MPI size. And then we wish to know, okay, I am a process, and what is my unique identifier amongst all the processes that have been started. And then you use MPI rank, okay? And you get your rank, and then you printf or you print the rank and the number of process. So hello world, I am rank something inside of a group of something process. And of course, at the end of your application, you clean up everything. So you call the MPI finalize function and you return the value of success. We are very happy the application successfully run. So how to compile this program? As I said, MPI in itself is just a library, it's not a compiler, but there is a wrapper. So a compiler is called by a script with all the necessary linking to necessary flag in order to link to an MPI, to link to the MPI library. And on the Med, for example, if you want to use OpenMPI, you first load the module, so OpenMPI 3 in this case. And as you can see, there is also a mention of GCC. So it means that you will use the OpenMPI library, and the host compiler will be GCC. And then you compile your program with the wrapper, which is MPI CC, okay, for a C application, and MPI F90 if you were in Fortran. So it adds all the compiler, this script, MPI CC, all the compiler flag needed to link to your library, endpoint MPI library. So if we go, you can see that if you do MPI CC show, you get what these MPI CC commands means. So as you can see, it's just a standard call to GCC, but then you have a lot of flag, which is of course the include flag and the linking with the MPI library, as well as where to find this library inside the file system. So it's just a script that called GCC. This is the idea between this MPI CC or MPI F90 comment. And of course, because it's just a standard code to the host compiler, you can put any flag that is valid for this compiler. So if you want to specify that the name of your executable, you use the -o. If you want to optimize to the level 3, you use O3. You can use all the compiler flags that are valid with your compiler. You use your compiler exactly as if you compile your serial code, but you just use MPI CC in order to be sure that everything is perfectly linked with the MPI library. Now about running an MPI program on a CC cluster. You create your job submission script, Slurm submission script, and the idea is that the end task will indicate the number of processes that you want to run. So as an example, you specify that you a nice job name, the time, and then you say, okay, I want 4 processes. So I put end task to 4, and then I specify that I want 1 CPU to be allocated for each task, some memory, the partition, and the output that where we want to send the output of our program. And then I load the MPI module. I do the classical CDI to where I submit my script. And then you have MPI run. And MPI run is a script that will launch your application, the multiple instance of your application, depending on the environment in which it is running. So it's just a very useful command to start your MPI application. And then you have the -np, which will specify the number of processes that you want to start with MPI run. And in this case, I use the Slurm environment variables in order to use exactly the same value as the value as specified in the end task argument for Slurm. And then, of course, you have your call to your executable. So these commands say, okay, I want to run Slurm end task times Helloworld in parallel. So it will start Helloworld Slurm end task times. Okay, so for the Helloworld, if we want to compile this Helloworld that we have just presented, you compile it with MPI CC. And then, of course, you can just run it as it, and it will start on 1 process. And the result of this is that you will get hello rank from rank 0. There is only 1 process. And of course, the only rank available is 0 out of 1 process. Now, I want to run this application in parallel with 4. Then I use MPI run, specify that I want 4 process. And the result is that I have 4 output out of my Helloworld program. 1 output from the process 0, and then the process with rank 1, 2, and 3. And if you run this program multiple times, you can see that the order of this print is different. Of course, in parallel, you cannot expect that everything is going to be exactly as your. Okay, I will go back to the Slurm use for the question that just popped. Okay, so as you can see, you run your program multiple times. In parallel, you have different output because in parallel, you are not sure about how many. You are not sure in which order your process will execute the code. So of course, every time you run your code, you will have different output. Sometimes it's rank 1 that is the first one to print. Sometimes it's rank 0, and so on. So what exactly didn't you well understand about the Slurm use? Because it's difficult to know exactly what's the problem. Just say, I don't understand Slurm use, but can you be more precise about what? You take care of that, Damien, I see. Okay. Is there something really related about? Yeah, okay. So there was a question about Slurm, but it will be taken care of. Okay. So the idea is that when you have your job submission script, you will just submit it to the cluster with the sbatch command. And as I specified that this output should be in MPI hello out, then when I do a cat on my MPI hello, I will get the result of my program. Okay, but I see that you want to know how to use it, but I cannot do a full course about how to use Slurm. This is not the topic of today, so I'm sorry I will not answer this question. This submission script was an example for Le Maître 3 with a specific module available on Le Maître 3. You can use MPI application on any CC cluster. And of course, on Hercules and Dragon 2, you will be restricted to one node. Le Maître 3 allows for multiple node jobs, so jobs running on multiple machines. On Hercules and Dragon, it's not the case. But anyway, you can run an MPI program inside the same node. And then the process will be distributed amongst the sockets and amongst the core available on this CPU socket. So of course, in Hercules and Dragon, you have no real communication through a network, which is the case with Le Maître 3 if you run your job on multiple nodes. And here you have the list of the module available, at least for MPI version 3 with GCC 8. You can see that the list is really limited at the moment as Vega just died, and NIC 4 is in restricted access, and NIC 5 will come later this year or beginning of next year. So that's the idea behind the basics of MPI and how to write an Helloworld. So you write your Helloworlds, define, and you start to check out your number of process and your rank, so your identifier, and then you run it on the cluster using Slurm and defining the number of tasks, which define the number of process that you will start. But so far we have done no communication, not explicitly at least, and this will be the topic of the next chapter. So point-to-point communication. As I say in the introduction, in MPI you start your application in by starting multiple processes that run in parallel. But these processes have different address space. A variable that is defined and the value of a variable that is set on one process is not available in the second process, as well as the memory allocated and the value you put in this memory is not available to the second process. So you need, in order to make data available to a second process, you need to have communication. And the idea of communication is that you can take a piece of data that is stored in the address space of the first process and you copy it to the address space of the second process. And this is done through a message. And this message will just contain the data, but also an envelope saying, okay, it's supposed to go to there. This is the size of the data. It contains also information about the message and the message in itself. And the way you can see that is like an email, okay? In an email, you have different fields. First, which is the from field. So who is the sender? You have a to field, where it's supposed to go. And then you have a subject that identifies the type of message. So you can order thing and be organized and say, okay, this is about this subject, this is about another subject, and I have a kind of a conversation that can have some follow-up. And of course, you have the message in itself. And in MPI, how it's done is that the from field is equivalent to the sender rank, so the rank of the process that will send the data. The to field of an email is the receiver rank. And the subject is defined as being the tag. So the tag is just a number in MPI, but it's the equivalent of the subject in an email. And then you have the message, which is the piece of data that you want to send to the other process. So that's the basic idea of what we need to have a message in MPI. And sending a message is done using the MPI send function. And this MPI send takes several arguments. The first one is a pointer, an address in memory to the data you want to send. And then you have two things about the number of elements and the type of element that you want to send. So you have an integer, that is the count, so the number of elements of a certain data type. We will see the list of the available data type by default. So a data type is the type of data you want to send. Is it a double? Is it a float? Is it an int? Is it an unsigned int? So this is the basic idea of the message. I want to send the data located there. And this data is made of count data type, count element of a certain data type. And then you have the rank of the process that is supposed to receive the message, so the destination of the message. And then you have a tag which identifies the type of message, so this is the subject of the message. And you have a communicator, as the process can be part of multiple communicator and have a different rank depending on the communicator they are part of. The consequence is that if you specify a destination rank, you have to know in which communicator you want to communicate in order to be sure that it will go to the right process. And on the other end, you have a receiver, and this receiver receives the message using a call to the MPI receive function. And the MPI receive function is very similar to the one used to send a message. The difference is that except the void address, it's not where the data you want to send, it's this where you wish to receive the data inside the receiver process memory space. And then you have count and data type. And basically, we will see that in the next slide is that the count is the maximum length of the message that this process can receive. This is not exactly it may be different from the exact size of the message. This is the maximum length that the process can receive. And then you have the source, which is the rank of the process that make the send call. So identifying who is sending the data. I want to receive from rank something. And then you have the tag, so the subject of the message, a communicator, and you have a state2 object, which is an array of integer in Fortran, which contain information about the message that has been received. And as we have seen, we have in these two functions, we have the MPI data type, which is in Fortran an integer, which is the kind of data that you want to receive and that you want to send. And these data type are defined by the MPI standard as constant, and you have constant for different type of data that are available in C, for example. So if you want to send a char, you say that this is an MPI char. If you want to send a float, it's an MPI float, MPI double. If you want to send a double. So you have a list of available default data type defined in the MPI standard. And in addition, we will not do that today. You can create your own custom data type. So in Fortran, it's exactly the same. You have a specific data type that are defined I see that I forget something there because you have in Fortran an MPI double precision data type if you wish. But if you have you use MPI double, you will have no trouble. It's equivalent to that. So it's not a problem to use MPI double or MPI double underscore precision. It's exactly the same. So this is the data type. No more about the receive buffer. As I said, the count in MPI receive is the maximum number of elements that you can receive. And so as a consequence, the memory that needs to be allocated to receive the message should be large enough to hold the message. If not, the behavior is undefined. But the buffer, the receive buffer, may be larger than the data you will receive. So the count argument is just the maximum number of a certain data type that the buffer can contain. And the number of data elements may actually be less than what you specify in the receive function argument. But it cannot be, of course, if the buffer is way too small, for sure you will run into trouble. So that's the idea. And then we have seen that in the receive function, we have the MPI statue structure. And this MPI statue contains information about the message. So the source, the tag, and the error associated, if there is any error. And also with this MPI statue structure, what you can get is information about the message. As with the receive function, you just specify the maximum size of the message that you can receive. If you want to know exactly what's the size of the message that has been received, you need to do a call to an MPI function in order to know this information. And this is done using the handle that you get from the communication, the MPI statue handle. And so you use the MPI get count function. You pass the statue that has been filled when you receive the message. You say, okay, this was a message with this data type, and then you will get the count as the value of the variable you pass as a pointer there, count. Okay. And of course, the data type you use in the MPI get count needs to be exactly the same as the one you use in the receive function. And if the number of elements received exceed the limit of the count parameter, then when you call the MPI get count, you will get an MPI undefined. So this is also a way to know that your buffer was too small if the size of the count when returned there is defined, is set to MPI undefined. So let's go into practice and see some code because it's probably very abstract. So we will do a variant of the hello world, but in this case, we will do an hello mate. And we define a buffer to store a message, which is defined there. And we get information about our environment. You want to know the rank of our process inside this environment. But then, depending on the rank, we will do differently for each of the two processes that we will start. For process with rank 0, we will copy hello mate inside message, and we will send it. So we will send, this is the address of the message that you want to send. This is the length of this message. Of course, in C, you need to do +1 because you have the trailing 0 at the end of the string. We will send strlen message +1 MPI char. Okay, we want to send it to process 1 with tag defined as 99. This is not important in this case, but I just choose a random tag. And I want to do this communication for all the process, so in MPI world. And then I print, okay, I send this message. For process with rank 1 now, it will be the receiver. And what we say is that, okay, I want to receive a message there in message with maximum size of 20. This is of type MPI char. And I want to receive it from process 0. And then we use exactly the same tag so that it match. The send and receive tag should match. And we do that inside MPI world, and we pass a pointer to the statue handle that we have created there. And with this handle, we reuse it with MPI get count so that from this statue and knowing the type of data that we receive, we can get the number of elements that has been received. So if you do that, I don't remember the name of this file. Oh, I think that's it. Okay. So we take this code, we compile it, and then we run it on two processes. And we get this. Process 0 send hello mate. This is this part of the program. Process with rank 0 will execute this part of the code. And process 1 received hello mate. So this is what we have done there for process 1. And as you can see, even if we specify 20 there, which is the maximum size of the buffer, when you use MPI get count, you get a size of 12, which is the actual size of the message with the trailing 0. Of course, this is 11 character with trailing 0. This is not the case in the Fortran version. The size of the message will be 11. Will be 20, sorry, because I just fill it with a space. So this is the idea between for the basic send and receive example on two process. So this is exactly what I just described. So even if we specify a maximum message size of 20, the actual size of the message that we received was 12 in C. But in some case, you may say, okay, so I have to guess what will be the maximum size of the message that I will receive. It can be very painful, so maybe I will allocate too much memory every time. So you can do differently using the MPI probes function. So the idea is to probe, as the name said, the message before receiving it. And for this function, you will specify, I want to receive a message from this source with this tag inside the communicator, and give me some information about the message. So the idea is that if you have a simple program that will send a buffer of size 3, okay, you want to know the size of this buffer on the receive size. So as rank 0 will send this buffer, and then you have rank 1 that will probe this message before allocating the memory. So we do that. We probe the message from source 0 with tag 10 inside MPI.com and we get the statue. Okay, and then from this statue, we can get the count. So the size of this message. Okay. And then you can allocate the buffer, knowing that the size of the message. So I allocate the buffer, and then I do the MPI receive call with the buffer I just allocated, with the count I just get from the probing of the message. And I know that I will receive MPI integers from rank 0 with tag 10. So this is a way to get information about a message before doing the actual receive call. But let's say that you don't know a lot about what is going on. You don't know the source and you don't know the tag. You can do a very savage MPI probe using MPI any source wildcard or MPI any tag wildcard. So saying I don't care about the source and I don't care about the tag. I just want to know if there is a message somewhere that is in need to be received. So we do again an Hellomate where we send this message, and then we do the MPI probe from any source with any tag inside MPI.com world. And from that, we know nothing prior about the message, except that it will be a char. And then we use MPI get count in order to get information about the message, and in particular the message size. Okay. And from the statue, you can also get the source and the tag. And this is exactly what we do. We allocate a buffer to receive the message. Check that it's not MPI undefined. This is probably unnecessary in this case. And then we do the receive with the information we get from the probe. So we allocate the receive buffer. We have the message size that we get from MPI get count. And then you have MPI char. At least you know that. And then from the statue that we get from the probe, we can specify that the source and the tag of the message that needs to be received. So this is a way also to receive a message with no prior information. Okay. So in summary, to send a message, to send and receive a message, you need to do two things. One process needs to send a message, and another process needs to be ready to receive this message. And this message is identified by a tag, which is the subject of the message. And when you do a send, it needs to identify to who you were sending the message to. On the other hand, for the MPI receive call, you need to have a matching tag and specify from who you want to receive. And on the receive side, you will be specifying the maximum message size that you can receive, but it doesn't need to match the size of the buffer that you send on the send size. So this is a summary of what we have just seen. You can get the actual message size using MPI get count and the status, And you can also probe the message and know a little bit about the message before receiving it using the MPI probe function. So that's a summary of what you have just discussed. Okay, let's do a simple example to illustrate the idea behind the single program multiple data. We'll do a very simple program that is doing nothing really interesting, but it's basically a sum of numbers inside a range. So we just do the sum of I from 1 to n, and this will be the serial code. Now, if we wish to do that in parallel, what do we want to do? We need to divide the work among the processes, and each process will compute the sum on a certain range of integers. Once the sum for each process is computed, we send the partial sum to the process with rank 0, for example. We can choose a process, arbitrary process, but in this case, we send this to rank 0. And then from rank 0, we will computing the final sum. So the first step is to divide the work among the process. So each process will define a range of integer on which it needs to work. So we use the size of the communicator, so the number of processes that are working, to divide the work, and we use the rank to determine the range of data in which we want to perform the work. So that's the basic idea. You can find out the start and the end on which your process need to work using the rank and the size of the communicator. So you define, this is kind of a magic formula to every kind of work that you want to divide. You can use the rank and divide by the com size in order to define the start and end of your range of data. So that's the basic idea. So you first define your start index and end index. And for each process, it will be different because each process has a different rank. And we do +1 there because we don't want to sum. In this case, we don't want to have a start index to 0 because proc sum will be 0 plus 0. This is useless in this case. Okay. And we define the end index, the same thing. So start index and end index will be different for each process because they all have different rank. And then we do the actual work on this range defined for each process. So we defined a variable, and this variable is defined inside a process memory space. It's not shared at all. Each process has its own version of procsum, and the operation that is performed on this variable will be private to each process. It's in the memory space of the process. No, the other process don't have any idea of the value of procsum at that time. But now, if we want to compute the final sum, we need a way to take all the partial sum computed by all the process and send them to one of the process that will do the final operation. How can we do that? For arbitrary amount of process. We decide that the rank 0 will do the final work. And so every process with rank superior to 0 will do a send. We will send the partial sum owned by each process to a process with rank 0. And then process with rank 0, okay, will collect all these removed sums and add them to its own sum, the sum that it compute before that. So we have n-1 call to the MPI send, because of course you have n process, but rank 0 is not included in this send, so n-1 process will do the send. And of course you need n-1 receive call in order to collect all this data. So we do a loop, a for loop, and this will be the source of the message that we want to receive. Okay, static to 1, because we don't want to receive anything from process 0. and the rank is between 0 and word size -1. So we do this loop between these bounds, and we increase the source, of course, in the loop, and then we do the call inside this loop to the MPI receive. So this is where we want to store the data that we will receive from each process. This is of size 1, MPI unsigned. This is the source, so it will be different at each iteration of the loop. So it will be 1, 2, 3, 4, 5, depending on the number of processes that you have. And there, this is the tag that I choose arbitrarily, and you have the communicator in which we communicate and the statue object. And then from this remote sum, we add it to the sum that is located in the memory of the process with rank 0. So here you have the complete code. And what is very nice doing this is that even if you have only one process running, it will be no trouble for you. So if you don't run this application in parallel, it will be just fine. The start index and end index will be exactly the range of data that you want to work with. And of course, in this case, there will be no process with rank superior to 0. So this will never be called. And the same thing applied there, of course, because word size will be 1 and SRC needs to be inferior to 1. So this loop will never do any iteration. So all this part about communication will just disappear if you run it on one process. So your serial, the code can run as a serial application if needed. So you have the complete code also available in the archive that I put on Indico. All the examples that are presented in the slide are available on Indico through the MPI example zip, and you can download them and test them. Most of the times they're way more complete than what I present on the slide because of the space I have. Okay, so in the previous example, we just demonstrated a very basic strategy of dividing the work among the process. And this is a common strategy for MPI application, which is subdivision of the computational domain. And depending on your application, depending on if you want to really scale up or not, some domains can have equal size or variable size. So you may have adaptive domain size that vary it with the iteration. Most of the time, you try to have the same amount of computational work for each process so that your workload is balanced. And of course, one of the rules also is that you want to minimize the amounts of data that needs to be communicated. And I will explain why later in this session. And depending on your problem, you may use different domain decompositions. They come in many shapes and size. You can use a cuboid, binary trees, quad trees, oct trees, pencil slabs, anything. So when you design your application, sometimes you need to go with pen and paper and just think about, okay, I have these data, I have this problem. How do I divide the work among the process? What will be the best strategy? How do I minimize the communication? At which time this process will need this data? So you need to do a lot of work before writing your code in order to write an MPI application, because there is a lot of things that goes behind it. So let's talk a little bit about communication performance and the different communication modes available in MPI. Nothing is free, and communication comes at a cost. And this cost is can be described with this formula. So the time for communication will depend on the latency, which is the inherent cost of the communication. So you can see that as the time needed to send a message with a zero size. So it's the time needed for all the setup in order to have communication to occur. And then you have something that is dependent on the size of the message you want to send. And the peak performance, so the asymptotic bandwidth of the network you are using in order to send your message. Okay. And from this, we can compute an effective bandwidth. So the bandwidth that you actually get when you transfer a message of a certain size. And you can see from this, so it will basically the size of the message divided by the time to send this message. So this is exactly the same as the TCOM there. For a very small message size, the bandwidth you will get will be dominated by the latency, because this part will be very small. If the network has a very high asymptotic bandwidth, then this part will be very small. And as the message increase, then the effective bandwidth will be we have less and less dependency on the latency, so the time needed to set up your communication, and will reach a point that is slowly increasing towards the maximum transfer rate of your network. And we can visualize this with a very simple program, which is described as the ping pong program. The idea between this program is that you have two processes. One will send a ping, so a message, and the second process will take this message and send it back to the process to process 0. It is a pong, and you do that again and again. And in our case, I do this 50 times, and then you measure the time, and you can determine the transfer time of one message and change the message size and see the effect of the message size on the effective bandwidth that you get from this program. So the idea there is that this is a loop for the size of the message. Okay. So the message will increase. We will send 27 messages that will be increased in size. You have this program in the example archive that is on Indico, and we measure the time between for a ping pong. So basically, we send a message, and from process 0 and process with rank 1 receive this message, and then send it back to process 0 that will receive it. And n is the size of the message that we will increase, and we do that 50 times. And it allows us to do an average of the time to get to do a ping pong operation. Okay, so of course we do we send a message to 0, and we send a message we send a message from rank 0 to rank 1, and then from rank 1 to rank 0. So of course we have 100 message that is sent. So we have to take that into account. And we measure the time, as you can see, with the MPI wall time function that I described at the beginning of the session. Okay. What we get is this. Notice that this is a logarithmic scale. So of course, if you use a linear scale, this curve will be way more asymptotic. And here you have the bandwidth in gigabytes. So this is what we measured. And this is a ping pong program that runs on NIC 5 that will be available hopefully next month, and if not, at least at the beginning of next year. It will include 70 nodes with EPIC processors, 56 gigabytes of RAM, and 100 gigabits per second InfiniBand interconnect. So what we see there is that with very small message size, the bandwidth is completely determined by the latency. So we have very, very low effective bandwidth. But as we increase the message size, then we get more and more until we reach the theoretical performance of the network, and you can see that it really starts to be at the peak performance for message size superior to 10 megabyte. So you have to take that into account. If you send a lot of small message, you have to know that the bandwidth you will get will be dominated by the latency, so the inherent cost of sending a message, and because the message is so small, the transfer rate will be very low. So you have to think about it and find a balance between sending the number of messages you send and also the size of the message that you are sending. And then you have different communication mode in MPI. The default one, the standard one, will be either synchronous or buffered. What it means is that synchronous, the MPI send function will only return when the receive is completed. This is the synchronous mode. And then you have the buffered mode. It complete even if the message is not received. It's the message is set into an internal buffer, and this buffer will be used to send a message, but it's not. But there is no guarantee that while this message is in the buffer, the message has been received by the receiving end. And the standard sense, and the one we use, can be either synchronous or buffered. It depends on the implementation. It may depend on the message size. It may depend on the network. It may depend on a lot of things. So you have to be aware that when you're using the standard MPI send, it can be either the MPI send will block until the message is received at the other end, or it will be stored in a temporary buffer and send when the receive buffer is ready. And then you have also a mode that is less useful, which is the MPI air send. It always complete, and it needs to have a matching receive a call ready. So this is what it means by ready. So you need to have a receive before the send in order for this communication to occur. So this is the different mode. And the fact that the MPI send can be either buffered or synchronous may lead to very strange behavior concerning deadlocks. And this is what we will discuss now. So as I said, MPI send is blocking sometimes if it uses the synchronous mode. So it means that it's blocking until the message data and envelope can be safely stored. And safely stored can mean stored in a temporary buffer or received by the receiving end. And this is what the definition of completion inside in MPI. Completion means that the send buffer can be safely reused. So you can modify the buffer, there will be no consequence because the buffer is either already received by the receiving end or has been stored safely inside an internal buffer used by the MPI library. But if it's in a temporary buffer, it's not already present in the receiving process memory, or it may just be copied into a temporary system buffer and just waiting to be sent. And if we use the synchronous mode and that the MPI send is blocking until we receive the message is received, then we can have a deadlock. So if you consider this piece of code, when we do a send on both the process with rank 0 and the process with rank 1, then the process with rank 0 will wait if MPI choose to use synchronous mode. We'll wait until process with rank 1 is ready to receive the message. But the problem is that rank 1 is exactly doing the same thing. It's just waiting for process with rank 0 to send a message. And we end up with a process that are just waiting for each other, and we have a deadlock. So it's a state in which each member of a group is waiting for another member. So we are stuck. And the MPI receive call will never occur because the MPI send is just blocking, waiting for someone to receive the message. So of course, the obvious solution is just to do the opposite. So this is what we have done with the ping pong code. We send for the first call is a send on rank with process first we do a send on a process with rank 0, and we do a receive in a process with rank 1, and then the opposite. So this is a way to solve this problem. So you have to be very careful about the order in which you do the send and receive call, because you may end up with deadlocks if no one is ready to receive the message. And we will do an illustration with a problem which is a cyclic allo exchange with a cyclic, an allo exchange with cyclic boundary condition. So this is quite common problem if you are doing, for example, stencil calculation on a grid of points. You will divide your grid and assign a part of the grid to each process, and if the updates need some value on the right or on the left on the grid, you need to have an allo exchange in order to collect the updated value from one process to the other. So this is a communication where basically we just take a piece of the data on the first process and send it to dedicated part of the memory in process 2, and then we do the same with process 3 and process 4. So that's the idea, and the last one send it back to the first process. If we do that with a very simple call to the MPI send and MPI receive, okay, we'll do a send. If we consider the red arrows, we do a send to the right, okay, and then we do a receive if you consider the blue part from the left rank. And as a consequence, of course, you will end up with a deadlock. If you have 4 processes, they all will call all the send in order to do this operation, but you are stuck because the MPI receive call is not done until the send is finished. If we consider a problem with no cyclic boundary condition, it may be better, okay? But, so in this case, if we just consider the red arrow, okay, the last one will not do a send, okay? So we need to take into account this fact. So we have an if there. Rank needs to be inferior to size -1. And then the first here will not receive anything. It will just send to the blue part there. And so it only need to have a receive. Okay. So it will be better. But if we choose to have synchronous communication, then you have this kind of pattern. And basically, the process with rank 3 will be the first to receive, so it's perfect. So it will leave process with rank 2 free to receive, and then we continue like this, and we have some kind of serialization of the communication. So the serialization occur in steps, subsequent steps. So the communication time will be quite high. For that, to avoid the deadlock, if we have cyclic boundary condition, or avoid serialization, we can use non-blocking communication. And this is done using the I function, I send and I receive function. And this I means for immediate returns. And it allows to perform the communication in 3 phases. So initiate the non-blocking communication with either MPI I-send or MPI I-receive function. And this function will return immediately. And then you can do some work if you wish, and then wait for the non-blocking communication to complete. So this function very similar to the one with the standard one. So without the I and with a capital S there. Okay, so we have the address, the count, the data type, the destination of the message, the tag, the communicator. And then for the MPI send, we have something new, which is the request. This is the handle of the non-blocking communication. This is something that we can use to check afterward if the communication did indeed finished. Okay, and you have exactly the same for the MPI I receive, and then the statue is replaced again with this request that will be very helpful in order to determine if the communication did complete. So this MPI request is the very important thing about this non-blocking communication. When you make the call to MPI I send or MPI I receive, you will get this MPI request back. It is generated by this function, and you can use them with either MPI wait or MPI test. It means that with MPI wait, you will just do exactly what it says. You will wait until the communication completes. With MPI test, you just test if the communication did complete, but MPI test will return, while MPI wait will just block until communication is complete. And of course, one of the consequences of doing non-blocking communication as the send function or receive function return immediately, you have to be very careful. You may not modify the send buffer because, of course, then you will alter the data that is sent. So you have to be very careful to not modify the send buffer before the send operation is complete. And for the non-blocking receive, you have to be very careful not to read the buffer before the receive operation is complete, because potentially the data in the receive buffer in this case will be garbage or not initialized, or at least not the data you expect. So you need to either wait or at least test if the send or receive operation is complete when you use non-blocking communication. So this is the MPI wait. It takes the request that we get from the non-blocking communication call, okay, and then it returns the status of the completed communication if it's completed, and it will wait until the request that you are probing finished. Okay, so for example, again, this is a cyclic communication, and we will do a ring communication where we will basically do sum of all the rank inside a communicator. So what we will do is that each process will store its rank in the send buffer and send the rank to its neighbor on the right. Okay, so of course I represent this as a ring. So we have a process with rank 0, it will send its rank to process with rank 1. Rank 1 do the same, it send to process with rank 2, so it send 1, and so on. And each process receives this data and sum it to a local variable and repeat. So of course, in the step 2, then the value in the send buffer from process 1 will be the value you received previously from the process with rank 0. So it will send 0, while process with rank 0 that received 3 in the previous step will send 3 to process with rank 1. And you continue like this. And as you do this, once you have completed the ring, so everyone receive data the rank of everyone, you should have in the local memory of your process the sum of the rank, and this sum should be the same for each process. Okay. If we consider a synchronous version, we can choose to have the rank which is inferior to the last possible rank to first send and then receive. And then for the last rank in the group, we do a receive first and a send. So we avoid a deadlock. So this is a way to do ring communication in synchronous mode. And of course, if we don't do that, we have a send and a receive, and the send will be blocking until someone is receiving, and we don't have this if, and all the process do exactly the same thing. No, we will have no transfer. It will be stuck in a deadlock. And the problem there is that, as I see, this is the last process, the last rank. Okay, this is it will receive first, and then it will, as receive, process 2 is free to do the receive. So process 2 will be at this part. Okay, so again, you do he can do the receive. He will get from process 1, and so on. But the problem is that we are serializing the communication as we have seen before. So this process will be quite slow because every time we do communication, it's one step at a time. We have the communication does not occur at the same time for each process. Each process has to wait for the process with superior rank to be ready to receive the data. If we do that in an asynchronous way, we can just say, okay, I will send, and don't worry about the send to complete right now. So I do the immediate send, it returns, and then I am ready to receive. Okay, but of course, for the next operation, I need to modify the send buffer. So this is the point where I need to wait. I need to wait because in the next step, I will modify the send buffer. Okay, this is synchronous, so we don't wait for this. It's not a problem. It will only return when it's received the data. But this one return immediately, and we modify the send buffer. So we have to be very careful, and we have to wait for this request to complete. Okay, and then we can do the operation. So we have the send buffer, and we put the receive buffer. So at the next iteration, it will send that, and we do the sum in order to have the sum or the all sum of the rank inside the ring. And what will happen this time is that MPI sum return immediately, and then all the processes are ready to receive, and then we can have the communication that occur in a way that is way more asynchronous and more direct, as we don't wait for the MPI send. But of course, we have the MPI wait here that is required in order to be sure that every communication is finished and that we can modify the send buffer. And if you modify the code in order to just send a big chunk of data, you can really observe this slow process in the case of the synchronous send, where with the serialization, if we increase the number of processes, then of course we have more steps to do in order to complete the communication with the synchronous send, and the time needed to send data around the ring, to complete the round trip, will increase with the number of processes, and this is something that we don't really wish to have. Of course, in the asynchronous send, the time will increase, but it's because we are sending more and more data, as the time to do the loop will increase with the number of processes. If we look this, of course, there it will be dependent on the number of processes. So we do more iteration. So of course, the time to send 1 gigabyte inside this loop will increase, but as you can see, this is fairly linear with the size of the number of process, while in the synchronous send, we end up with a serialization of this process, and it takes way more time to send the data around this loop. Where blocking communication may be also very useful is to avoid too much waiting time when we have a load imbalance inside your application. For example, if you consider two processes, one represented in blue for the work of this first process and the other one represented in green. If you have communication at some point and you wait for the process in green to receive the data, you have a blocking send that can take a large part of your application runtime, just waiting for the second process to be ready to receive data. And the same is true if, as the blocking receive may wait for the process in blue to send the data, and then you have a lot of waiting time that is not needed or not desirable, at least. This is one of the reasons why you try to have very, very well-balanced amounts of work between the process to avoid to wait a lot for communication to occur. But sometimes it's may be very difficult to do this kind of load balancing. And the idea behind this is that you want to hide the communication with, so that the cost of the communication is almost invisible. And in this case, seriously, the cost of communication is very high, and it's very high because the transfer, the waiting time between the transfer and the moment where the data is ready to be sent is quite high. So ideally, to hide this, the time spent in the calculation need to be large enough to hide the communication, even if you have waiting time. But if the time spent in the calculation is way higher than the time spent in waiting for data to be ready to be received, then it's quite okay. And of course, you can try to overlap the communication and computation. So no communication and communication. I'll write 2 times the same thing. And you can do that with asynchronous communication. So if we consider one-dimensional diffusion problem, so this is a very simple stencil calculation. The actual calculation is done inside this loop. Okay, so we update values with the values on the left and on the right of the value we wish to update. This is the idea behind it, and to do that we need the value on the left and the value on the right. So we have kind of a halo exchange, as we have discussed at the beginning of this chapter. And if we use the non-blocking communication, what we can do is the following. We need the value on the left to be transferred at the beginning of the array of local to the process, and we need the value on the right process to be stored at the end of this array. Okay, so we do to receive. So basically we ask for the process that owns the left value to send it, and the same for the process that owns the right value. Okay, so we have 2 calls to MPI I receive, and then we have 2 calls to MPI I send, because we send our own value, okay, to the left and to the right. And what is interesting there is that this value that we send and receive are not needed for all the points. So we can just start at 2 instead of starting to compute to the left. And we can ignore basically the value that we are supposed to send and receive for the moment. So do the calculation first and update these points, so the first one and the last one, in a subsequent step. So we just initiate the communication, do computation that are independent on the ghost point. And then only when we finish the calculation, then we wait for all these requests. And in this case, what I use is an array of requests. So I create an array of 4 requests, okay? And I use a different value in this array for each of the call. And I use the MPI wait all. Okay, so I say that I want to wait for these 4 requests. Okay, and I get an array of status at the end of this call. And then when I know that this all communication is done, that I have received the value I need, I can update the point on the leftmost and the rightmost side of the local array for our problem. So that's the idea. You can wait for multiple requests, and you just use the MPI wait all with the number of requests you want to wait for. Okay, and then you pass an array with the request we wish to wait, and you will get an array of statuses at the end of this call with the information about the message that has just been transferred or sent. Okay, I did go way too fast. We still have half an hour, but if I start collective communication now, we'll not finish until, okay.